Okay, welcome back. In this lecture video, we're going to look at example 3.2, still on the delivery time data. Now, in the previous example, we looked at how to estimate some of the parameters in the linear regression model, the multiple linear regression model for this data set. In particular, we looked at how to estimate the intercept and the slope coefficients, in other words, the beta coefficients for the model. In this example, we're going to look at how to estimate the remaining parameter, which is the variance of the error term in the model. Now, before we do the calculations, I want to look at the notes about this. And so if you go to section 3.2.4 in your textbook, they give a formula for calculating what they call the residual sum of squares. It's also called the error sum of squares, or the sum of squares error, typically denoted by SSE. You might remember from previous courses. In this textbook, they denote it by SS res for residual in the subscript. So we can denote it either way. In my programs, I'll probably be denoting it by SSE. So one of the formulas that they provide for calculating the residual sum of squares is given here on this slide. The difference between the inner product of the observed response vector, in other words, y prime y, minus, and then this expression here is basically, well, it's a combination of the predicted y values, or it's the inner product of the predicted y values and the observed y values. So beta hat prime times x prime is a vector that contains the predicted values, and then we are looking at the inner product of that with the observed, or the value of, sorry, the vector of observed values. Now that's an algebraic simplification of another formula. Let me see if I can point you in the direction of this other formula, and we'll see this in the program. Let's see here. So we could look at this right here, and this is the least squares criterion function that we minimize in order to get the least squares estimators of the slope coefficient, or the beta coefficients. And if we were to put hats on these epsilons, we would then have the inner product of the residuals. Putting hats there, we would have to put the hats on the betas. And this gives us perhaps a more direct way to at least think about what that SSE, or how that SSE is calculated. But again, that does simplify to this formula that they give in this section, so right here. So we're going to calculate it both ways, and just to verify that we do get the same exact value, regardless of which of those two formulas that we use. So this gives us the sum of squares residual, or the sum of squares error. And then once we have that, we divide that by the number of degrees of freedom associated with the error term, and that is given by or equal to n minus p, where n is the number of observations and p is the number of parameters, beta parameters in the model. So let's take a look at this, and I'm going to be using two different packages, statistical packages, again, as in example 3.1. I'm going to use SAS. I'm also going to use MINITAB because they use both of those in the textbook, and I happen to have both of those on my computer. And in using SAS, we're going to use two different procedures. Again, as we did in 3.1, we'll use PROC IML to really look at the internals of this calculation and implement the formulas that they're giving us in the textbook. And then we'll show a quicker way to do it using PROC Reg. So let's see how to use PROC IML in SAS to estimate the variance of the error term for this multiple linear regression model. And so again, I invoke PROC IML, the interactive matrix language in SAS, and I have to I have to get the data into PROC IML. And currently what I'm doing is I'm entering the data, both the response vector and the design matrix, as matrix literals, as we discussed in the previous previous lecture video. In subsequent lecture videos, we'll see how to bring that data into PROC IML in a different way. But this is fairly straightforward. And so this is how we continue to do it. So we won't spend any time looking at this. We've already spent some time on that. Okay, and then again, I do like to print out a listing of my data, just kind of visually verify that it's been input correctly. And then what we're going to do is we're going to, again, perform the calculations for estimating the model parameters, in particular, those beta parameters, the intercept and the slope coefficient. In doing these calculations, this time, however, I'm not going to print out the X prime X matrix, the inverse of the X prime X matrix. I'm not going to print out the X prime Y matrix and so forth. I'm just going to calculate these quantities, and I'm going to store these intermediate or these intermediate calculations in intermediate matrices. So, for example, I'll call the X prime X matrix XPX. The inverse of that X prime X matrix as XPX underscore inverse, and also the X prime Y as XPY. And then in this example, I am going to use those saved matrices in calculating the parameter estimates, right? And so you can see how we can do that looking at this line right here. And it's often helpful to do these different calculations piecewise, just to make sure that at each step things are being done correctly. If you get a really long expression, it's possible to have things specified incorrectly, and then you've got to chase down errors and things like that. And so this helps facilitating getting through the calculations and doing it correctly and not having to spend a lot of time chasing down errors. Okay, so again, what we're going to be doing here is first estimating the parameter estimates, because we have to have the fitted model before we can calculate or before we can estimate the error variance. All right, so we will calculate the parameter estimates, the beta estimates. We'll print those out. And then what we're going to do is we are going to estimate the error variance using two different formulas. We're going to use, the first formula is going to be the more direct way to think about how to calculate the sum of squares error, at least in my view. And then we'll also calculate it using the formula given in the textbook, which is, again, an algebraic simplification of the first formula or the definition formula. And then we'll compare the values just to, make sure and to demonstrate that you get exactly the same thing. So, whichever one you like to use, you're free to use it. But I just want to show you both formulas. And by the way, since I'm using two formulas, and I want to compare the values obtained by those formulas, what I'm going to do is I'm going to create two different variables, one for each formula. And we're going to call those variables MSE1 and MSE2 for the first and second formulas, respectively. Okay, so here is how we're going to implement or do the first calculation, that which I'm calling Formula 1. The first thing we would need to do is calculate the predicted values of y. Now, the predicted values of y, which I'll store in a vector that I'll call y hat, all right? We calculate the predicted values of y by multiplying the design matrix X times the least squares estimators of the beta parameters, so that beta hat vector. Once we have that, we will continue on. Now, I'm not going to print that out. I'll print it out subsequently. But once we have the vector of predicted values of y, we're going to construct the vector of residuals, model residuals. And we'll call that vector of residuals E. And we get this by subtracting the predicted values from the observed values. And so we take the y vector and from it subtract y hat. Now, once I have that, then at this point, I'm going to print out the observed y values, the predicted y values, and then the error, the residuals, the model residuals. Now, once we have the model residuals, then we can take their inner product or their dot product, all right, and that dot product or inner product gives us the SSE, the sum of squares error, or as your book denotes it, the sum of squares residual. And again, because I'm using two different formulas, I'm going to label this one SSE_1. All right, we'll print that out. And then once we have the that sum of squares, we can divide it by n minus p to give us the corresponding value for the mean squared error, which again is the estimate of the error variance based on this approach. Now, how do we easily get programmatically obtain the number of observations and the number of parameters? Well, that's easy. For example, we know that the y vector has dimension n by 1, n being the sample size. And so we can just query that vector or apply this function, the n row function, to that vector, and that will give us the number of observations in that vector. The number of parameters here, the beta parameters, is given by the number of columns in the X matrix. And so we'll use the ncol, NCOL function, applying that to the design matrix X, and that will give us P. And then once we have it, we calculate the MSE, and then we'll print that out. Now, on to the second formula. And this is the direct implementation of the formula in the notes. And so let me just scroll back over here. This is the formula that we're going to be implementing in Formula 2. And so I first calculate y prime y. All right, I'm going to calculate that here, and I'll go ahead and print that out. And then once we have y prime y, we subtract from that beta hat prime times x prime y. Now, beta hat prime is just the transpose of beta hat. And so, and again, I'm using the transpose function here to obtain that transposed matrix. And then we multiply that by x prime y, which again, I've already calculated and saved in the XPY matrix. So that gives us the sum of squares error, or the sum of squares residual, based on this formula. And then once we have that, we divide it by n minus p to give the mean squared error based on this particular formula. All right, and then what we'll do, we want to compare those just to make sure that, or to demonstrate that they give the same exact value. And so I'm going to print out not only MSE1 and MSE2, but I'm going to calculate their difference, all right, and print that out as well, just to make sure that there are no differences, in some of the smaller order decimal places. Okay, so that's what we're going to do here, and let's go ahead and run this. Okay, and so let me just scroll up here, and we can see here we've got the listing of the data as we had before. And again, what we're doing here is estimating the error variance. Okay, and then we went directly to calculating the parameter estimates. Once we had the parameter estimates, we were able to calculate the predicted values of y, which are in the second column of this matrix. So the first column would be the observed values of y. The second column is the predicted values of y. And then the difference between the two is, would be the residuals from the model. And so that's those residuals are given in the last column. Now, in order to find the sum of squared residuals for using the first approach, we're going to take the inner product, or the dot product, of that last column of values. All right, and when we do that, we get 233.73168. Now, again, what that's doing is it's taking each of the values in that last column, squaring those values and adding those squared values up. And that is 233.73168. Then once we have that, we divide it by n minus p. All right, and so n would be 25 in this example, p would be 3, and so we're dividing by, we have 22 degrees of freedom for error. All right, and so we divide that 233.73168 by 22, and that gives us 10.624167. So that is the estimate of the error variance for this model based on this first formula. Now, for the second formula, we're going to be applying or utilizing this formula. And so I've calculated y prime y and printed that out. And that's equal to, let's see, 18,310.629. I'm not printing this quantity out. It's just a little bit too cumbersome to assign a a label to. I suppose we could do it, but if you want to do it, I'm going to give you this program so you could modify it and do that. That would be a good little exercise for you. But when we take the difference, when we calculate this and take the difference between y prime y and that quantity, we get the sum of squares error based on the second formula, and that is 233.73168. Well, that's the same exact value we got using the first method. All right, so that's great. And then we divide that by n minus p, we get the same value for the MSE, 10.624167, which is exactly what we got using the first method. And I print both of those values out down here at the bottom, and along with their difference, and we can see that there's no difference at all. Okay, they're the same exact value to the precision of the software, and that is the case because they are algebraically equivalent. So any differences that we might see would just be due to rounding. Okay, so that's how we can calculate the estimate of the error variance, the variance of the error term in the model. And again, that estimate is 10.624167. Now, let's see how we can use PROC-reg to obtain the same value. Now, we have, I'm going to use PROC-reg, and I've got to create a temporary data set. And so I'm doing that here. We've seen how to do this in the previous lecture video. And then I have PROC-reg down here, and I've modified some of the selected features that I want to, or some of the options that determine the selected features that are going to be displayed in the output. And so, and I put some of these on different lines so that I can more easily put comments out here to describe what is, what's what does what. And so we can see here that I'm specifying, well, first I'm still, suppressing the plots. I don't really want to see those right now. So plots equal none, we'll suppress the plots. I have my multiple regression model, y equal to x1 and x2. And then notice that I've got an option, a slash here, because I'm going to include a few options. And the first option I want to show you how to use is the XPX option. That's a keyword in SAS and in the context of PROC-reg. And what that does is it tells PROC-reg, it instructs PROC-reg to include the X prime X matrix in the output of PROC-reg. In addition, I've got the I option to the model statement, and that instructs SAS to include the inverse of that X prime X matrix in the SAS output. Now, as I stated in the previous lecture video, PROC-reg, if we just use the defaults, it's going to print out a bunch of stuff. And if we include the, these additional options here, it's going to print out even more. I really want to focus in on just a few things, a few parts of that output. And so one way that I can, well, the way to do it is to use the ODS select statement PROC reg. And so what this is going to do is limit the output to the cross products table, the table of cross products. It's going to include the inverse of XPX in the output. And it's also going to include the ANOVA table for the regression. Now, if I had not included the cross products or the inverse XPX in the ODS select statement, then it would not have included the XPX and the inverse of XPX in the output. It would have generated, well, it always generates it, but it would have not have displayed it. So again, yeah, I'm kind of doing two things here. I'm asking for this extra output, but then after that, I'm suppressing everything except what's included in this ODS select statement. And so let's run this and see what we get. Okay. And so the first thing I want to point out is this table here. And this table gives us the cross products, the model of cross products. And it tells us here in the title of the table what it actually gives us. It gives us the X prime X matrix. It gives us the X prime Y the X prime Y matrix or vector, and it gives us the value. Technically it's a 1-by-1 matrix, but it's we think of it as a scalar, Y prime Y, which is the uncorrected sum of squares of the observed values. Okay. So let's take a look at this, the structure of this table. In this case, the first three, well, these rows intercept X1 and X2, and the corresponding columns intercept X1, X2. That 3-by-3 subtable is the X prime X matrix. The last column, and in particular, the first three rows of the last column gives us the X prime Y vector. If we look at the last row, the first three columns give us the transpose of the X prime Y vector. So it would actually be Y prime X. And so you can see here that we've got 595.6 up here. We've got the same thing down there. We've got 7375.44 here. We've got the same thing there. And then finally, that value is equal to that value. So this subvector here is just the transpose. This row vector is the transpose of that column vector. And then finally, the entry here in the last row and last column, that's the uncorrected sum of squares of the response vector, Y prime. This is Y prime Y. All right, now let's look at this next table labeled X prime X inverse, parameter estimates, and the SSE. So this 3-by-3 subtable gives us the inverse of the X prime X matrix. In the last column, the first three rows give us the actual parameter estimates, and you'll recognize these, you'll remember these: 2.34, 1.62, 0.014. All right, those are the parameter estimates, beta 0 hat, beta 1 hat, and beta 2 hat. And then the entry in the last row and last column, that is the sum of squares error. All right, that you'll remember we just computed that using PROC IML, and they show here 233.731677742, and so that's the same value to that. It's equal to what we got using PROC IML. And then finally, I included let me show you here. I included the ANOVA output, the ANOVA table output for PROC reg. And the reason I'm doing that is because I wanted to get this value right here. That is the mean squared error. Okay, that is the estimate for sigma squared for this regression model. So again, 10.62417, right? And that's what we got using PROC IML. By the way, you will also see the sum of squares error, all right, here in the ANOVA table. That's that value right there. So let me just show you, if we were to, let me just comment out. Let's see here. The cross products and inverse XPX from the ODS select statement. The only thing that would be produced is the ANOVA table. And you can see here that we could get the mean squared error from that and really not have to clutter up our output with the X prime X matrix, X prime Y, Y prime Y, and then the inverse and so forth. All right, but if you want to see those values, if you want to see the X prime X matrix, if you want to see the X prime Y matrix, if you want to see Y prime Y and so forth, then you can. All you need to do really is just include those two options to the model statement. And in fact, if if we were to comment out the ODS select statement, you're going to see here that it just generates quite a bit of stuff, right? But if we uncomment that, we can select, we can suppress everything except what we say that we want to see. Okay, so that is how we can use PROC Reg, PROC IML and PROC Reg, all right, to get an estimate of the model error variance. I also want to show you how to use MINITAB to do that. And so here we have, again, let me take a look at the data here. So this is the data for this example. We've got 25 observations. We've got delivery time Y, number of cases X1, distance X2. And if we were to, in selecting the regression, all right, and if we go to results, if we tell it to include the analysis of variance table, all right, then we're going to get that analysis of variance table, and we can see here that we have the mean squared error, 10 point, and they're displaying this to 2 decimal places, 10.62. And we also see the sum of squares error. And so you see that we can get those two values, but in particular, we can get the estimate of the error variance, which is in this case 10.62. Okay, that's the MSE in the model. Okay, so that is how we can go about doing this, and we will continue on looking at this data, analyzing this data, using some other. Well, before I stop this, let's go back and look at the example. So we can see here, this is from the textbook, and we can compare the values that we get to what they get. And you can see here that their estimate of sigma squared is the same that we got, 10.6239. Okay, so that is all I'm going to talk about in this example. We've got some additional examples, and we've got some subsequent sections to cover, and so we'll do that in subsequent lecture videos.